Welcome back. In our last explainer, we dove into the power of linear regression, but we also hit its biggest limitation. It kind of assumes the world moves in straight lines.
But real-world data is almost never that simple. It curves, it bends, it's just messy. So what are we supposed to do when our data refuses to play by those straight-line rules? Well, let's jump in.
Turns out, the answer is this really clever technique called polynomial regression. This is the key that lets us model all those complex, nonlinear relationships we see out there in the wild.
And here's the absolutely brilliant trick at the heart of this. We're going to model a complex curve, and you got to get this part, we're still using the same linear regression engine we already know. The model is still linear when it comes to the weights it's learning. By creating these new polynomial features, we're basically giving our simple model superpowers to see things in a whole new dimension.
So how exactly do we pull this off? It's really just a four-step trick. First, you start with your plain old feature x. Then, and this is the magic, you create these new synthetic features like x squared, x cubed, and so on. Then, you just pop these new features into your equation. And finally, you train the model exactly like you would any normal linear regression. We're essentially inventing new information from our old data to give the model way more flexibility.
This slide just lays it all out perfectly. Look on the left, the standard linear equation can only ever draw a straight line. That's it. But on the right, just by adding that one little x squared term, we've totally transformed the model. It's not stuck drawing lines anymore. It can now bend into a parabola and capture a curve. Pretty cool, right?
Okay, so this new power is incredible, but it immediately creates a huge new question. I mean, we can add x squared, but why stop there? Why not x cubed? X to the 4th? Heck, why not go all the way up to x to the 15th? How much curve is actually too much curve? And that question, my friends, leads us to one of the most fundamental ideas in all of machine learning.
This whole thing brings us to what's called the bias-variance trade-off. Honestly, the best way to think about it is as the Goldilocks problem of machine learning. We're always searching for a model that's not too simple, not too complex, but just right.
So first up, let's talk about bias. Bias is basically the error you get from a model that's just too simple for the job. It makes the wrong assumptions from the get-go. Imagine trying to trace a winding river with a ruler. The ruler's core assumption is that things are straight, so it's going to be wrong, consistently. In machine learning, we call that underfitting. And then you have the other extreme, variance. This is the error you get from a model that's way too complex, way too sensitive. A high-variance model is like an artist who doesn't just draw you, they draw every single piece of lint on your shirt. It memorizes the training data, including all the random noise, but it completely fails to learn the bigger picture. We call that overfitting.
Okay, let's see this in action with our Goldilocks analogy. Here's our first bowl of porridge. It's too cold. This is a polynomial of degree 1, which is just a fancy way of saying it's a straight line. It is way too simple. It has super high bias, and as you can see, it just completely misses the obvious curve in the data.
And here's the second bowl. This one is way too hot. This is a super high-degree polynomial, maybe something crazy like degree 15. This model is so flexible that it just wiggles and squirms all over the place trying to hit every single data point perfectly. It has high variance, and it's capturing all that random noise, creating this chaotic line that has zero chance of predicting anything new.
And finally, the third bowl. This one is just right. A moderate degree polynomial, like degree 4 in this case, finds that perfect sweet spot. It's complex enough to capture that essential curve, but it's simple enough that it ignores all the distracting random noise. What we're left with is a smooth, clean, generalizable curve.
So this table really just puts it all together for us. Look, when the polynomial degree is low, the model is too simple, and we're stuck with high bias or underfitting. When the degree is too high, the model's too complex, and we get high variance or overfitting. Our whole goal as a data scientist is to find that sweet spot right in the middle, that balanced model with low bias and low variance that gives us a genuinely good fit. Here's one last analogy to really lock this in. Think of building a bridge. A super simple blueprint is going to be structurally inaccurate. That's your high bias. But a ridiculously detailed one that includes every single pebble on the ground, it's going to be flimsy and unstable. That's your high variance. A good model, just like a good blueprint, builds something strong, reliable, and just right for the job.
Okay, so we've covered a lot of ground, from creating synthetic features all the way to this Goldilocks problem. So, when it all comes down to it, what's the one thing you should really remember?
The big idea is this.
Polynomial regression is our ticket to modeling the curvy, nonlinear world. But that power isn't free. It forces us to face this bias-variance trade-off head-on. Our success totally depends on finding that perfect degree of complexity to create a model that actually learns the pattern, instead of just being too simple or memorizing all the noise.
And that leaves us with one last really important question. I mean, it's great to know we need to find the just right model, but how do we actually do it? How do we systematically find that perfect Goldilocks degree and stop our models from overfitting? Well, in our next explainer, we're going to explore exactly that, the techniques we use to tune this complexity and keep variance under control, making sure our models are both powerful and reliable. See you then.